Well, I was notified of my Nobel Prize in the middle of the night, not by the Nobel people, not by Stockholm, but by a radio station in Boston, WEEI. And they said to me at 5 o'clock in the morning, "What are you going to do with the money?" And I said, "What money?" And they told me that I won the Nobel Prize. I never did hear directly from the Nobel people until the mail arrived. But it was a wonderful experience when I went. It is held every year, the Nobel ceremony on December 10th, which meant that on my birthday on December 5th, I was flying with my wife and my four children and my two brothers and my au pair girl to Stockholm. Uh, and we had a wonderful few days before the ceremony. And then I received this large piece of gold from the King of Stockholm, King of Sweden. It was a wonderful pleasure. Now, what did it have to do with? I have to go backwards in time to explain why I got the Nobel Prize. So if I go back all the way to 1932, that was the year the neutron was discovered. It's the year that the positron was discovered, and it is the year that I was born. And some years later, when I was in high school, I decided that I wanted to become a theoretical physicist. And so did my friends. I'll just call them Steve and Gary. And when we finished high school, Gary went off to Columbia, and Steve and I went to Cornell. And that all of us became majored in physics. And Steve and I separated after college. He went to graduate school at Princeton, and I went to graduate school at Harvard. And so I remained until I got my thesis. That was in 1958. And I was planning to go to the Soviet Union after graduating, and I had plans to be at the Lebedev Institute, but the Russians, the Soviets, never sent a visa, so I was never able to go. Instead, I wrote to Niels Bohr blindly and asked him if it would be possible to visit his institute. He said, yes, by all means, come. So I came to Copenhagen, and I would end up spending quite a long time there, the first 2 years, supported by a National Science Foundation fellowship, the kind of fellowship that Trump has done away with. And it was in Copenhagen in 1959 that I wrote the paper that won the Nobel Prize for me. So that happened when I was just a kid. Then many other things happened, and then I was 26 or so, 27. Now I'm 92. So there's been a lot of happenings in my life and in physics. And what has happened in physics and astrophysics in that period of time is absolutely spectacular. There's been so much progress and so much excitement. For example, in my field, when I entered, we studied the weak interactions and the electromagnetic interactions separately, and the gravitational interaction as well. But today we know that we have a semi-unified theory of weak electromagnetic and strong nuclear forces. That is a remarkable achievement. The particles like K mesons, which were very mysterious, Ks and lambdas and sigmas, were a crazy bunch of particles that uh, firstly were fit into families by Murray Gell-Mann, who became my mentor when I went to Caltech after Copenhagen. And I wrote a wonderful paper with Murray Gell-Mann as well. But uh, I was very impressed by his theory, which he called the Eightfold Way, in a joking fashion. And I spent a lot of time in the next few years, helping to implement his theory, putting the different particles that were being discovered at Berkeley uh, into representations of SU3. Anyway, after uh, Copenhagen, I went to Caltech for a year as a postdoc, but then I wanted to be a professor. So I managed to get an assistant professorship at Stanford. And after that, I, uh, I only spent 1 year at Stanford. I went to Berkeley, where I knew I would get tenure. And it was at Berkeley that I found the next uh, instructor, key mentor to my life. The first one was my advisor. I didn't have time to mention him before, at the great physicist Julian Schwinger at Harvard, and it was he that taught me field theory in a language that it was difficult for anyone to understand. Uh, and then my second, and yet he inspired me. It was he who told me to set out to find a unified theory of weak and electromagnetic interactions. That was the subject of my thesis. I did not succeed in doing it, but I made some progress. So I managed to get my degree and went off to Copenhagen. By the way, in Copenhagen, I met the Soviet consul to Denmark, and he was a very engaging young man. He would give us vodka that he brought from Russia. He would come to our parties. He would always say, "My visa coming soon." Actually, my visa came never. Years passed and there was no visa. So I forgot about going to the Soviet Union until years later, 64, I think. In 1964, I visited Dubna at the major conference in particle physics. Well, my first mentor was Julian Schwinger. My second mentor at Berkeley, at Caltech, was Murray Gell-Mann, who became a very good friend until he passed away a few years ago. And then I went to Berkeley and met my third mentor, who was an experimental physicist, Luis Alvarez, who was the head of a group that was finding new particles. And I was having fun putting these particles into the theory of Gell-Mann. Anyway, finally, I got offered a job I was very happy at Berkeley, but there were problems. There was the free speech movement, which evolved into the filthy speech movement. There was a lot of political activity and little time for science. So I went to Harvard, and I remained at Harvard for many years. I got there in 1966 and I left in 2000 and did many of my own papers there. And particle physics was evolving rapidly in 1973, jumping 73, well, 64 was a spectacular year for particle physics. Many things happened in that one year, and I can barely remember which. One was astrophysics. It was the discovery of the cosmic background radiation. Another was the violation of CP symmetry. CP is a combination of charge conjugation and mirror symmetry. So CP is you change yourself into antimatter and you look in a mirror. And the laws of physics seem to be invariant under that transformation of reversing time and looking in the mirror. But in 1964, it was proven to not be true. Another friend of mine introduced the notion of quark color. Quarks had been introduced in 1964 by Murray Gell-Mann, and the notion of quark color was introduced in 1964. And I introduced the charmed quark in 1964. In Murray Gell-Mann's theory, there were two doublets of leptons, one doublet of quarks, and one leftover quark. And we decided there had to be another quark so that there could be two doublets of leptons and two doublets of quarks. In other words, we introduced lepton-quark symmetry, which remains a symmetry of physics today. So many things happened in those years. The work in 1973, not at all my work, was the formulation of the quantum theory of the strong interactions, the gauge theory of what's called color SU3. And that, after many years, turned out to be accepted as the theory of the strong interactions. Its many successes became overwhelming, so it is now universally accepted. At that point in the 1970s, we had the beginnings of a partially unified theory of strong, weak, and electromagnetic interactions in terms of one rather complicated gauge group, Lie group. It's a continuous group, like the group of rotations. That particular group is called SU3 cross SU2 cross U1. And that became the basis to what became known as the Standard Model, which explained a great deal of particle physics. In fact, no experiment has ever been done that contradicts the standard theory. It's not a sufficient theory. It leaves a lot of questions unanswered. They remain unanswered today, unfortunately. But as far as experimental success is concerned, it's 100% successful. There was, just a few months ago, you could have said, what about the magnetic moment of the muon? It was measured and it was theoretically computed, and the two things did not agree. There was a problem, and people were happy because it's necessary to have a problem in order to solve it and make a better theory. But it turned out just a few months ago that the experiment was repeated with the same result as before, and the theorists found an error and got a corrected result, and now experiment and theory are in complete agreement with one another. So the last obstacle to the standard theory of strong, weak, and electromagnetic interactions has disappeared, and we have no flaw to build upon, which leaves us rather confused. Meanwhile, in the subject of astrophysics and cosmology, they too have developed their standard model. I began to become aware of the standard model back in 1973 when Steven Weinberg, with whom I had shared the Nobel Prize, would share in 1979. In 73, he wrote a wonderful book called The First 3 Minutes, which I recommend to you. I'm sure it's been translated. And it gives a wonderful introduction to what has become the standard theory of cosmology. There's a new edition after 1972 because a lot happened since, and that's more or less included in his revised book. But also in cosmology, there are severe unresolved problems. We don't understand the nature of dark energy, which causes the universe to expand again very rapidly, and dark matter, which causes the galaxies to have masses 10 times greater than the sum of the masses of the stars in the galaxies. So that this missing mass is called dark mass, and the stuff that causes the universe to expand is called dark energy. And those remain mysteries. So there are mysteries that were solved. There was a wonderful mystery that came about in the 1970s, which was called the solar neutrino problem, which went on for a long time until it was finally solved by experiments done in Japan and Canada. And those experiments showed that neutrino oscillations explain the very strange results that neutrino physicists had observed for many years. So that was a problem that was solved, and many problems were solved. And we now have a sort of situation which is very frustrating because we have a theory of particle physics that answers all the questions we can ask experimentally, but not the questions we can ask theoretically. And we have a theory of cosmology, of the origin and evolution of the universe, which has some difficult questions, such as dark energy and dark mass. But there are others having to do with the very nature of the very early universe. As I say, things have gotten more exciting in the years since I was born. The space telescopes now exist, huge space telescopes, the most recent space telescope being the James Webb telescope. And they have peered more deeply into the universe than any telescope that has existed before and discovered many puzzling things about the early universe. Namely, that too many galaxies seem to have formed too soon, and we don't quite understand how that happened. Another great discovery that I didn't mention took place in 1967. That was when a young lady in England observed pulsars. She saw in the sky something that was flashing. It was flashing many times every few seconds. The first pulsar. So she discovered that particle, and her research advisor won the Nobel Prize for its discovery. But pulsars were very interesting things, which we now understand. I mean, they are rotating magnetized neutron stars, which spurt out a beam of energy which sweeps around, and sometimes we can see it each time the star rotates in the right way. So what we see as a pulsation is really a rotation of the star. That was an exciting discovery. Quasars were an exciting discovery, both of which we more or less understand. And pulsars have become very important in a completely different context. Let me jump back to particle physics. One of my good friends in particle physics that I met at a conference in Scotland with my family and his family and all our kids in somewhere in Scotland, and we became very good friends. This was Barry Barish, and Barry Barish went on to join the LIGO program after doing many other interesting things. And it was the LIGO program that discovered, was it 2017 or something like that, discovered the gravitational waves that had been predicted 100 years before by Albert Einstein, searched for many years by others, but he and his group managed to see many, now hundreds of instances of mergers of black holes, which are so violent. They are the most violent events that we know of as yet in the universe. And they produce, they put all of their energy into gravitational waves, which are very hard to detect. And he managed to succeed at detecting them. Now there's other people who have tried. The Italians also built a gravitational wave detector, which broke. The Japanese built a gravitational wave detector that doesn't work. The Indians are trying to build a gravitational wave detector, and Trump is trying to shut down the LIGO facility. So gravitational wave astronomy, the new and most exciting form of astronomy, is in deep trouble at the moment, mostly thanks to Trump. So is the rest of science in America, for that matter. It's very troubling. So is government, because when my friends invented quantum chromodynamics, which was the correct theory of strong interactions, I was talking about pulsars. There is now something called the pulsar timing array, which is a group of many radio telescopes throughout Europe and in other continents as well, in North America as well. And this array of pulsars measures pulsars from many different points and can detect small changes in the pulsar frequencies. And that results from very large gravitational waves. These are attributed to the gravitational waves, not of merging stars, but of merging galaxies taking place in the early universe. And we still don't understand how that came about early in the history of the universe. So it's all tremendously exciting, and there are all kinds of things going on, not necessarily in particle physics and not necessarily in cosmic physics, as astrophysics, but in all kinds of physics. The verification of of the failure of classical physics by the what's called the Bell inequality experiments were done in the 70s or 80s that showed that classical physics doesn't work, that quantum mechanics has to be true. And that kind of work is continuing and is very exciting in the context of entanglement, which you've heard about. And it's again merely a consequence of the same quantum mechanics that was invented by Heisenberg and Schrödinger and others many years ago, but it's been experimentally demonstrated in many contexts and is very exciting. And there are all kinds of exciting things happening left and right, many of which win Nobel Prizes. I'm fascinated, for example, in quantum dots, which are another attribute of quantum mechanics, which has found many applications. I'm fascinated by graphene, which is a new form of carbon, which was also earned a Nobel Prize. So lots of interesting things are happening, and even though I'm more or less retired, I'm still very excited to read and learn about what's going on now.